Let me get started by making a brief introduction for this project and this presentation. I'm happy to introduce the work that has been done. This is about implementation of the internally cured high-performance concrete. Uh, this project has been sponsored by the New Jersey Department of Transportation, and we want to acknowledge their support and thank them for their effort in making this work a really state of the practice work. Since we have also developed the different mixes, but we also went further in terms of trying to do some field implementation, and we have a couple of bridges that are slated for this work in the future. Before I give the microphone to my colleagues, I'd like to first acknowledge the partners. I am the principal investigator on this project, so Rutgers took the lead, but we also had great support from NJDOT. Professor Muhammad Mahgoub was involved, especially in the durability aspect of the work, and Professor Khan Osbey and his team at NYU, who were also instrumental in trying to make the life cycle cost analysis and to help the implementation side of it. And I will also acknowledge other industry partners. This would not have been done without their tremendous support. In particular, I'd like to acknowledge Northeast Solite for their extreme help and support in getting the material and guiding us on some of the work that we have done. Clayton, who also implemented some of the mixes at their plant, and they delivered the concrete based on our work in the laboratory. Euclid Chemical and Sylvie, who are also instrumental in supporting us for different aspects of the project. The work was done really by the colleagues that are listed. Michael Rosala, who's really a research engineer. He's been with Rutgers as an undergraduate and as a graduate student, and now he's a full-time research engineer who really took the lead on this project and delivered most of the aspect of it. I want to also acknowledge Reed Holland, who's now graduated. He's a PhD already. Dr. Jacob Na, who's a senior research associate with our group, and Jenny Gao, who took the lead from the NYU side, and Arian Kaval, who really did a lot of work on trying to implement the spreadsheets and all the calculations needed for this work. And I want to thank C2SMART for giving us the platform and to provide this seminar today. C2SMART is a federally supported center with Dr. Khan Osbey, the director, and with Rutgers being part of that consortium, and with myself being the lead from Rutgers as the associate director for the center. So we've been having a great support on different projects, and the synergy between Rutgers and NYU has been established for the last 10 years, which, this product, I'm very proud to say that, and not to my surprise, that this product was a purely joint effort with all the partners today. So without any further ado, I want to thank you all for coming in today, and I'd like to introduce Michael Rosala, who's going to be speaking from the Rutgers side, and also Arian Kaval, who's also going to be covering the work that NYU has led and did on that one. So again, I want to thank you for attending, and I look forward to having you on future seminars. We have another seminar coming up at the end of this month, basically. So this is part of the BRB, Bridge Resource Program, in help with C2SMART, who are also doing the technology transfer part of that project. The Bridge Resource Program, for those of you who are not familiar with it, this is a program that the New Jersey Department of Transportation has been supporting, and we are also supporting the bridge group as well as other groups that are joining from DOT, including the Bureau of Materials that were instrumental in giving us all the support during this project. So without any further ado, I think Mike, you're going to be starting, right?
Yes, sir. Yeah. So
It's all
thank you
yours.
for the
Thank you.
introduction, Professor. I'm going to be talking about the development and field implementation portion of this webinar. So really, the most important thing to get started with is knowing when is internal curing beneficial. It is a fairly niche technology. It's typically used in applications with high cracking potential. This is commonly seen in HPC, especially when used in bridge decks and pavements. That's due to the highly restrained conditions that are typically seen in them, and this results in early age cracking, which is in some ways avoidable. This is typically due to a high degree of autogenous shrinkage in HPC, which results in this early age cracking. You can see on the screen a typical cracking pattern. And this is due to bridge decks typically having a high concentration of rebar, adjacent previous pores, shear studs, and all of these things at early ages before the concrete has developed proper strength and it experiences this high degree of autogenous shrinkage. It develops these stresses and results in this distinctive cracking pattern. And even though these cracks are typically fine transverse cracks, and they can be mitigated, they can be sealed over time, chloride ions do ingress, and it does result in corrosion over time and a decrease in bridge deck lifespan, and of course, an increase in maintenance costs and rehabilitation. So going into what the mechanism of lightweight fine aggregate is, it's effectively a porous sand that's used as a replacement of normal weight sand by volume. It acts as a water reservoir, so it doesn't affect the water cement ratio, but effectively allows more water to be introduced into the mix. As you can see with this diagram from Federal Highway, typical external curing only affects the top surface. HPC is a very dense material. It's not very pervious. So it doesn't get a cure throughout the or additional effective curing throughout the cross section. So this can result in a gradient, can result in different stresses developing, and increases cracking potential effectively. So one way to mitigate this is by using internal curing, where this curing compound or this curing carrier is dispersed throughout the cross section. It applies more consistent water distribution to the matrix, and it really does significantly reduce autogenous shrinkage, which we'll see in the upcoming testing portion. And yeah, so this has been seen to significantly reduce cracking. So we'll get into what internal curing carriers are available on the East Coast. So that's specifically of interest to the New Jersey market. So we tested the products in red, starting with Northeast Solite's product HydroCure. It's an expanded shale product. Most internal curing carriers are expanded shales. This is the most common expanded aggregate type. It's produced in New York, and the absorption is typical of this class of material at 18%. We also tested Statite. It's an expanded slate product. It's from North Carolina. It has a much lower absorption, so you require more of this material to get the proper dosage of the water inside the mix. And then there's the Arcosa product Riverlight, which is an expanded clay product from Alabama. It's a very light material. It has a very high degree of absorption at over 30%. So a lot less is required, but there's some strength, or really there's some durability considerations that we'll go into as well. And there's a more experimental product, HyZorb. It's a super absorbent polymer. So it's effectively like a water bead that you would put into this mix, and it releases the water stored in it, but it leaves a void, while these lightweight fine aggregates are effectively a stone. So that's a little bit of a difference. It's not these super absorbent polymers aren't very commonly used, but it is an interesting technology, and it's very straightforward to implement. So going into what other DOTs have used this technology. This isn't a new technology by any means. It's fairly mature. New York led the way in 2008, where several bridge decks were cast with this. And over the years, a lot of different DOTs have tested this material, and many have implemented it as well. So we have some of the products that were tested, some cases multiple, different types were tested in one study. But we found the performance change in these HPICs compared to the conventional HPC. So it's found that in most cases, the results were very similar. There wasn't much of a difference between the control HPC and the HPIC. That's favorable. We don't the workability was very similar, castability was similar, strength properties were similar. But one thing that was observed was in all cases a good degree of shrinkage was reduced, and in some cases a very high degree of shrinkage, especially with autogenous, which we'll go into a little bit as well. So summarizing those 16 DOT projects, it was found that internal curing HPC unanimously reduced cracking. Um, that was probably the main benefit, and that's what we're looking for, really. Any cases where it was less than expected was often attributed to improper saturation. So if it's not properly prepared, this material, before it's added, it can't provide the water into the matrix as expected. So really, it becomes a very critical to properly prepare these materials. And that's typically done using stockpiles. So a pile of material saturated by a sprinkler system over time. And then before use, it's allowed to drain prior and excess water to run off. Then you need to find what degree absorption this material is carrying. That's used. That's done by using ASTM 17161, and you can choose either the centrifuge method or the paper towel method. We extensively tested both. We preferred the centrifuge method. It takes the operator error out of the equation. It's faster, and you can get more samples done in a quicker time frame. So we prefer that, but of course you need the equipment, while the paper towel method can be done anywhere you have a person and paper towels. So that was something that we noticed and tested as well. So going into the experimental program, we did fairly extensive laboratory small scale tests. We evaluated expanded shale products, slate, clay, and SAP products. And we sought to highlight challenges and propose practical solutions as we saw them during our testing. So we extensively tested fresh properties. We definitely paid special attention. We want to make sure that this HPIC has similar castability to the regular HPC. We tested the strength is comparable, and we paid special attention to the durability properties. So that shrinkage, which relates to the cracking potential, the permeability of the material, so that's RCPT and surface resistivity, as well as free sol testing, which is a big concern with these lightweight materials historically. So we tested the paper towel method versus centrifuge method, and we tested different stockpiling methods, and we tried to replicate that as much as possible in the lab, how it would be in the field. So the solutions were we proposed the centrifuge method, and really the prep is what makes this technology excel. And you can get additional benefits by doing very good prep and just get more water into the mix. So regarding the dosages, there's a lot of discussion on what the proper dosage should be. Typically, that's resolved itself. It's mostly agreed upon that for the best benefit, you do 7 pounds of internally absorbed water per 100 pounds of cementitious material. So it's pretty straightforward to modify existing HPC formulations. So given a typical NJDOT HPC mix, 675 pounds of cementitious material per cubic yard, you can see the required dosages using these different materials. So hydrocure at 18%, you need something like 300 pounds. Styolite, lower absorption, you need something like 440. Arcosa with a very high degree of absorption, you require less at just around 200. and then the SAP product, which is effectively pure water in a bead form, just suspended in that polymer, requires even less. And there is a tool that's used for the dosing to quickly calculate it. There's the ACI 308213 graph method, which I'll go over here. So it's pretty straightforward. You'll know your base mix, so you have these properties effectively. So you have your cement con or cementitious content. You have your dosage, typically selected at 7 pounds of water per 100 pounds of cementitious material. So that's the CS. You know your water cement ratio of your base mixture, in this case over 0.36. And then you test the material for whatever its absorption capacity is, and there you have your dosage. So it's an easy way to double check and just ensure that that you're properly dosing your material. So going on to laboratory testing results, we tested 7 formulations during our laboratory testing barrage. We tested an HPC control and HPICs with expanded shale, slate, clay, SAP, as well as a field demo mix from Clayton that was delivered to our lab. So we had a typical HPC delivered, then a modified HPC with the expanded shale product, and that's the HydroCure product. So we found in all cases that the lightweight fine aggregates effect on slump and air content was largely negligible. Finishability was very similar as well. Lightweight aggregates require a volumetric air meter. It's specified to, but we saw a very small difference between the pressure meter and the volumetric meter. Results are very similar. We suspect this is because there's a very small dosage of lightweight aggregate compared to traditional lightweight concrete formulations. And this kind of shows itself with the unit weight reduction. We saw a very minor reduction in the unit weight of the concrete. Like we are using a lightweight aggregate, but we're not using all that much of it, how you would typically use with a lightweight concrete, with it being a full replacement of the coarse aggregate. So going on to the strength properties, we have all the mixes that we tested, the lab mixes that we tested. We saw that HPIC did better in all cases. A little bit different variance with the flexure strength, but with compressive strength, tensile strength, and elastic modulus, we saw that HPIC did as good or better. And in all cases, we saw the SAP did just a little bit worse than the control mix. That's expected because once again, these effectively water beads leave a void once the water disperses. So it's a little bit of a, I guess you could say, a defect is left and the strength is slightly reduced, but you do see a lot of benefit with the shrinkage. So you need to weigh these options. Regarding durability properties, we tested RCPT, so that's rapid chloride penetration test, as well as surface resistivity. For both of these tests, all the materials ranked in the low category, so that indicates a very dense matrix and a durable material. And this is typical of HPCs with this water cement ratio. So regarding freeze thaw, we tested the HPC control, HPIC with shale, and an HPIC with clay. We saw that the shale product performed very well. The clay product had a slight decrease. It still passed the test, which requires 80 durability factor for 300 cycles. So all formulations passed, but we did note that the clay product had a slight degradation with its durability factor. And this is to be expected. This clay product is typically used in the south of the United States, so freeze thaw isn't a high concern, and it excels in that environment. While in the Northeast, with our high degree of with our climate conditions and our high degree of salting, maybe that wouldn't be a priority material. So it's important to test these things early. So regarding shrinkage, which is kind of the whole purpose of this to reduce shrinkage and to reduce the cracking potential. With dry shrinkage, we typically saw less of a reduction, maybe more at early ages. But with the reduction in autogenous shrinkage is where these materials really do shine. You can see that for the early ages, shrinkage, autogeneous shrinkage was highly reduced. And this allows the concrete to gain strength before these forces develop in these restrained conditions that lead to the cracking that we're trying to avoid. So going into our field testing and demonstration, we had two mixes delivered to our laboratory. We had a typical HPC and a modified HPC delivered. We used these slabs with sensors affixed to the rebar. Slabs were left outdoors to cure in realistic conditions. And we tested two different curing methods. We tested 7-day wet curing with curing compound and traditional 14-day wet curing. And we compared the two at the end for some insights on that. And we use high precision strain gauges, vibrating wire strain gauges, and maturity sensors for this task. So going into the actual demo, we saw that the differences between fresh properties and workability were very minimal. Castability was about the same. There weren't really any differences when finished. You can see the material being discharged, and you can see the sensors being embedded into the mix and the curing practices and finishing that took place. And going into the strength properties of the field mix, we saw very good results. Um, both of these materials perform very similarly, and both had a high strength that was reported. And maybe the highlight of this program was the restrained shrinkage testing, which is both of these are a little bit of advanced test. We did the laboratory restrained ring test. So you can see these very clean results with a very high degree of reduction in shrinkage strain by the HPIC. And you can see that reflected in the simulated bridge deck slabs that had the sensors embedded in them. This was about 8 sensors for the HPCs and 8 sensors for the HPICs. So averaged together, you can see the result. It's a significant decrease in the shrinkage for those for the HPIC material, which in a highly restrained bridge deck, see a notification. Sorry, a highly restrained bridge deck reduces the degree of cracking and the forces that develop, specifically at early ages, which I'll go over in the next slide. So you can see that over time, the main benefit is at early ages, which is what we want. We want the concrete to be able to cure properly, gain strength without these strains developing. And we can see that as time goes on, there is a benefit that's maintained, but they kind of converge and kind of stabilize at around 30% past the curing window. And going into the comparisons between 7-day curing with 7-day curing with curing compound and the 14-day wet curing, we see that for both the HPIC and the HPC, these materials behave fairly similar. So it is something to look into as a possibility for accelerated construction, especially if you're getting the benefit with the significant reduction in strain for the HPIC. So I think that's about the stuff from my end. I guess I can hand it off to Aaron, and I guess we'll take questions at the end.
Yeah, so I'll start sharing on my end thing. Let me see the presentation. Okay, so thank you, Mike, for covering all this information. And now I'll be covering the life cycle cost analysis side of the things. So let me start off with what the project objectives were. So basically, Mike went over like the first 4 bullets, which were like the identification of a cost-effective practice of internally curing for bridge deck and concrete pavements for NJDOT, the There were reviews on neighboring states and DOT specifications, lessons learned, and the challenges of the current practices for internally cured HPC. And there were laboratory tests and also assessing technical feasibility and implementation of the material. And our end at C2SMART NYU, we wanted to see how we can perform life cycle analysis for the benefits that are expected for the specific material internally cured HPC. So this part of the research is devoted specifically to promoting the application and production of internally cured HPC in New Jersey. So first, I'd like to briefly talk about life cycle cost analysis and what life cycle cost analysis is. So LCCA is an engineering economic analysis tool that is going to be used to evaluate the total economic impact of different design, material, or maintenance options over the bridge's entire service life. It doesn't have to be a bridge. It could be any material, any structure. So the goal is to weigh these options over time. So why is this analysis important for our study? So it initially considers all of the agency expenditures and user costs throughout the entire life of an alternative and not just the initial investments. Additionally, it's going to be offering advanced insights on determining how the economic merits of the selected alternative is going to be presented. And finally, it is critical in evaluating new materials, new construction materials, techniques to quantify durability benefits and account for inherent uncertainty. So in this case, it will be critical in evaluating how HPIC is going to be performing against alternative materials such as HPC. So now I'd like to talk a little bit about our previous LCCA work at C2SMART. So we have previous LCCA experience spanning both technology-oriented transportation systems and bridge/material management applications. So our previous work has advanced LCCA beyond the typical practice by incorporating aspects such as uncertainty, time effects, obsolescence, and like different types of cost categories such as agency costs, user costs, social costs, etc. And our center has used stochastic multi-objective framework, like probabilistic approaches, which is used to connect project level rehabilitation planning with like network level investment decisions for various bridge assets. And throughout different projects such as recast and the use of Assist Me LCCA, our research was displayed on different types of web-based data-driven tools tested with NJDOT specific data, MBIS data. And basically the LCCA work has supported agency decision-making on new materials, repair strategies, like different network-wide project selection applications for bridges for partners such as the NJDOT. And one other big part of our BRP work is the NJDOT BRP project, where we focused on an Excel Python integrated tool, specifically working on bridge lifecycle cost emulation. So it is this tool was aimed to serve as a quick assessment tool to calculate LCC costs, LCCA analysis, and provide utility values for each individual bridge and analyze the whole network compatible with real-life cases and BRM results. So this was developed to serve as a quick assessment tool compared to BRM, the commercial tool, and it generates a set of actions that are going to be required to keep specific bridges within the network that is being analyzed from falling into poor conditions, and condition ratings are going to be ranging from 3 to 9, and the goal is to provide specific costs and utility values while keeping the bridges above a specific threshold based on internally encoded rules within the spreadsheet and the tool. And in addition to this initial functionality, we've made many improvements in order to improve the LCCA capability of this tool. And one important aspect is the Python integration of the optimization, where we added we connected Python using some packaging, and we improved data automation that helps put in NJDOT specific data, specific bridge database information in order to work with this tool. And we integrated risk scores and pre-filtration functionality so that the tool is much easier to use for an LCCA analysis, and integrating these optimization models both at the project and network levels while addressing for inherent uncertainties for various variables in this LCCA analysis. So now that I've covered some of our previous work, I'd like to now focus on how this research concerning HPIC has progressed. So in the context of HPIC, where Mike is also focused on, where enhanced durability aims to reduce shrinkage, cracking, permeability. LCCA is going to be serving as the tool where it helps us understand how these benefits are going to be helping the long-term economic value compared to other alternatives. So the following steps were taken in order to conduct this analysis. So initially, we have a deterministic analysis for a quick assessment on how the outlook is looking like for the materials. And afterwards, we wanted to see how uncertainty and how different types of variables can impact the life cycle costs of these two materials. So we want to see how these are going to be impacting the materials. Then we went into a probabilistic approach, and also we wanted to see how the CO2 emission for these two materials were going to be displayed based on the life cycle analysis. So some progression of the inputs and revisions. So initially, we used supplier and FHWA values for the LCCA analysis, and we were using Class A concrete as a baseline. And after getting some feedback based on what we heard from the NJDOT, we adjusted some of our costs and the service life assumptions, which I'll be talking about in a few slides. And we decided to remove Class A as it was deemed not relevant, as HPC was proven to be a superior alternative. And therefore, we wanted to specifically focus on how HPC and HPIC are going to be compared for LCCA analysis. And our final assumptions were adjusted to the NJ-specific conditions, such as high salt usage on roads and some of these conditions. And the bid prices were obtained for the new cost cases, and we wanted to use NJ compliant costs and conditions for the entire analysis. So here is a brief summary of the net present value analysis for a project level LCCA model. So here from this equation, basically summing up agency, user, and social costs, basically summing up various types of costs over the entire lifespan of the material or the bridge, and it uses a scheduled maintenance and rehabilitation action schedule and enforces feasibility via different types of deterioration functions. And if a condition is falling below a certain threshold, it's going to be requiring rehabs, replacement, and it's basically explaining how different types of costs are going to be accumulated. And in the end, it's going to be aggregated based on weights for different types of costs. It could be agency costs, traffic delay costs, and other crash risk costs. Different types of costs are associated with the entirety of the life cycle cost analysis, and all of these are converted to a net present value in order to do a final comparison between different types of materials. So we have some of the key variables, such as AADT, like the average daily traffic, truck share rates, and the cost function displays the per year time display for the direct and indirect costs, which are user costs, agency costs, and all those costs associated with the material for the life cycle cost analysis. Now, starting off with the deterministic analysis, we used a spreadsheet-based tool that was previously developed by the NYU RIME research team in order to integrate these life cycle costs analysis into an agency investment decisions. And we wanted to utilize this, as this was used for different types of analysis for multiple studies for NJDOT, Missouri DOT, and the recast project in the past. And estimates of the deterministic life cycle cost alternatives were analyzed using this tool. It has design variables such as FHWA recommended service life, supplier material costs, and other sorts of traffic and work zone variables within the tool. And the analysis was conducted for multiple bridges with various sizes, so that we can see how HPIC and HPC comparisons are displayed for different types of bridges and different sizes of bridges. So some of our inputs and assumptions for the deterministic analysis. So we have specific cost and service life inputs based on either NJ compliant cost information or FHWA estimates. So for HPC, since this is a more stable product, for the deterministic analysis, we start with the 1500 per cubic yard based on previous bid prices. And for HPIC, since this is a newer material, we wanted to have a set of costs so that we can do a sensitivity analysis to see how different types of costs from a lower end and a higher end can be compared to HPC based on all these information. So these costs are ranging from like a 10% increase based on supplier information. Like it's also for the middle end, we have a 20% increase based on the FHWA report. And finally, we have a higher end bid based on the higher end bid prices provided by NJDOT. And this analysis is incorporating multiple HPIC cost unit assumptions. And currently, at the time, which were likely elevated due to limited market experience, and the anticipated approach towards this is going to be around 10 or 20% increase once the material is going to be stabilizing. So for the cost assumptions, we have these values, and for the service type inputs, we have 25 years for an HPC bridge. And for HPIC, we wanted to use two types of service lives to see how HPC was going to compare with HPIC. So we first wanted to include a minimum end, which is 40 years, which is provided by NJDOT. And the second one, we wanted to use FHWA recommended information, which was set to increase the service life of concrete bridge decks for a minimum of 25 to 50 years. So we wanted to use the lower end of 25 and add to the 25 years of HPC to have a 50 years based on the minimum improvement threshold for the FHWA report. And we have some other assumptions about like the discount rate, which was obtained from OMB. And we have a 75-year analysis period for the entire analysis. Here we can see we wanted to have a few bridges from different areas to see how the analysis is going to be observed for different types of areas, different types of bridge sizes. And the maintenance schedule, finally, is something I'd like to emphasize on, because HPC, the HPC material bridge is said to be needing MNR actions every 5 years, and HPIC, which is the main benefit of the action, it will require less maintenance over the year. So it's going to be scheduled every 10 years, and some initial cost premium and other traffic data from the MBIS database, such as structure length, width, average day traffic, all this information was put into the tool for the deterministic analysis. And here are some of the results for the deterministic analysis. And using multiple bridges, we have agency costs for HPC yielding cost benefits around approximately 15% to 41%, depending on the unit cost and service life estimates, as you can see from the sample bridge information on the right-hand side. The sample bridge was taken from I-80, and we have a total cost information of HPIC displaying around 16 to 44% decrease. It's providing total cost benefits ranging from this. And if the unit prices are going to be stabilized in the future, as we assume, HPIC can achieve approximately 30 to 45% in agency cost savings under NJ conditions, such as high salt usage, as I mentioned. And here, in conclusion, HPIC, based on this deterministic analysis, is demonstrating lower network presence values, net present values for all of the costs compared against the HPC. And we should note that the total costs include direct costs, such as the agency costs, and indirect costs, such as vehicle delay costs, crash risk costs, etc., which are all defined within the tool based on all the information that I've provided as our input. So after this, we wanted to see how we can improve this by conducting a probabilistic analysis. And I'd like to talk about our inputs and assumptions based on this part of the analysis. So to account for inherent uncertainty, since some of these materials are new and we're going to be experiencing different types of fluctuations with aspects such as costs, and we can have different types of discount values, and all these variables might have some sort of distribution associated with them, and therefore are subject to some sort of uncertainty. So to account for this uncertainty associated with the new material, the probabilistic LCCA was performed, and the uncertainty was evaluated using Monte Carlo simulations, which are going to be involving repeated random draws from specified distributions of the input variables. So for our probabilistic analysis, we wanted to look into specifically the cost inputs as the probabilistic inputs, because we have a range of alternatives for both HPC and HPIC, which are going to be based on bidding prices, on the estimations and estimation support and historical statistics report. So we have all the lower end mode and the higher end value for a triangular distribution for HPC. And for HPIC, we have slightly higher minimum and mode values for the estimations of the cost, but we have the higher end similar based on the most recent bidding prices that were provided based on the information we have from November 2025. And the remaining inputs are kept the same as deterministic analysis, because we wanted to see how cost is going to be impacting, specifically the cost and its distribution is going to be impacting this type of probabilistic analysis. And the maintenance schedule, again, is going to be kept the same. And the two service life estimates are going to be used. So we're going to be conducting 40 years and 50 years for HPIC for different two separate analysis. And I'll be sharing the results right here. And here you can see how HPC and HPIC are going to be compared based on agency costs and total life cycle costs along their probabilistic distribution. So as I mentioned, Monte Carlo simulations were done. So we had 10,000 runs of Monte Carlo simulations to create these distributions from the defined input variables and the varying cost information. So when HPIC service life is set to be 40 years, so this is for the accounting for the lower end value of service life for 40 years, we have the probability of HPIC agency costs being lower than HPC agency costs over the entire service life and analysis of this project. This ends up as approximately 84%, and the probability of HPIC total costs being lower than HPC total costs is going to be 100% for all the simulated scenarios. So you can see the distributions. So basically, these distributions are created based on the 10,000 rounds of random draws of the distribution information that's being defined within the analysis. And you can see most of the time, like 83.8% of the time, HPIC is going to be dominating in terms of the cost, where the cost is going to be lower than HPC in terms of agency costs, and the total cost is going to be lower in 100% of the simulated scenarios. So going to the higher end service life estimation, which is going to be based on the FHWA minimum, 50 years, we see even higher probabilities of HPIC agency cost being lower than HPC agency costs, rises to around 96%. And we still have the HPIC total costs compared to the HPC total costs in 100% of the cases. So in conclusion, based on all this uncertainty and probabilistic assumptions that we provided within this analysis to account for the uncertainty for the different type of material, HPIC is outperforming HPC is in most of the cases for both of the service life assumptions and for both of the cost types that were analyzed. And now I'd like to briefly talk about how, the CO2 emission analysis for the social cost of carbon. So this analysis was done for different discount rates, where the social cost of HPIC was also investigated in terms of embodied carbon values. So initially, HPIC has a slightly higher social cost premium based on the information that's shared, and the social cost of carbon was assumed to be the following values based on some reports, which are referred to at the end of the presentation. So based on these results, we can see that based on these two discount rate values, we can see that the HPC social cost is going to be higher than HPIC, despite the initial extra embodied carbon a slightly higher social cost premium. HPIC has a lower social cost value compared when converted to net present value based on the social carbon, social cost of carbon assumptions. And you can see we have around 12% benefits with the 2% discount rate and 7.3% benefits with the 3% discount rate. based on two different assumptions to see how the sensitivity analysis can be made. So in conclusion, you want to look into different types of unit costs, service types, and additional HPIC construction costs and maintenance schedule inputs for the deterministic and probabilistic LCCA models, reflecting a range of NJDOT compliant conditions and also based on some FHWA estimates. And our results indicate that for the deterministic side, HPIC is showing agency cost savings of around 15 to 41%, and the total cost savings around 16 to 44% compared to HPC. And depending on unit cost assumptions and how this are going to be stabilized, the extended service life and reduced maintenance frequency, if the unit prices are going to be stabilized, HPIC is probably going to achieve approximately around 30 to 45% in agency cost savings under the NJ conditions that were considered throughout this analysis. And additionally, for the probabilistic LCCA analysis done by Monte Carlo simulations, confirmed that HPIC is robust to cost uncertainty, where agency costs are going to be around 84 to 96% probability that the HPIC agency cost is going to be lower than its compared alternative HPC for life cycle cost analysis values. And the total cost of HPIC is always going to be lower based on the simulations that were done. And finally, the social costs, despite the slightly higher embodied value, based on the net present value analysis, for converting this value into net present value, we have a lower social cost of HPIC compared to HPC, despite this initially slightly costly rent. Overall, our analysis based on deterministic and probabilistic analysis and also the social cost aspect have shown that HPIC is consistently outperforming HPC in terms of life cycle cost for various aspects of analysis. And some future work that we had in mind, so we wanted to look into some type of price convergence where we can model HPIC unit costs over time to an experience curve, so we can see when the material stabilizes, we can compare these values against different types of scenarios. And also we might want to look into the social cost of carbon aspect and the distribution and propagate these through emissions in inventory. And also we wanted to see as a future work how we can use different types of variables on top of the cost information. We can might use like different types of parameters for testing different types of uncertainty, and we might want to look into like different types of discount rates for different to see how life cycle cost analysis is going to be expanding upon these already made analysis. And finally, we might want to expand the bridge inventory that we're looking into to account for a larger set of ADT variables and regions to verify that the results are going to be observed for various traffic and logistic conditions. So here are some of our references. If you'd like to look into them once the webinar is concluded, if you can refer to them, some of the information that we used. And I think that's all I have for the life cycle cost analysis. So I think we can start off taking questions. But before we're done, thank you very much for listening. And we'd like to acknowledge, like again, like as Dr. Nassif mentioned at the start, we'd like to acknowledge the NJDOT Bureau of Research, Innovation and Information Transfer, and our partners, Northeast Solite, Clayton Euclid Chemical, and Sylvie, without whom the program would not have been possible. And now I think we can start taking some questions.
Thank you, Aaron, and thank you, Mike. Yeah, we are open floor for questions to all the audience. But before starting, I think you have two options. One, you can type the question on the Q&A at the bottom of the Zoom, or if you want to talk verbally, if you raise your hands, then I allow you to talk, and then Mike and Aaron can respond. But before doing so, there are three questions already on Q&A. Maybe Mike, is related to your part, the first two questions. Can you verbally repeat the question and then answer to that, please?
Yeah, so going off of Samer's initial question, he asked about the clay product and some details on the optimizing and why the shale product might have performed better, and if adjustment can be done to better leverage the clay's high absorption. And yeah, so with that dosage, it does account for the higher absorption. So it's 7 pounds of internally stored water per 100 pounds of cementitious. So it does already account for that difference. So they're all there's all that between all these materials, there's a baseline dosage. And as far as it being slightly less performance, it is a slightly weaker aggregate. It has a lower compressive strength. It's a more porous aggregate, which allows it to have that very high absorption. But there's also the consideration that it slightly can reduce compressive strength, and it being very porous doesn't help it with freeze thaw. And that's during our pretty extensive literature review, which I didn't really go into the literature review portion, but um, that was a consistent finding that we observed, that it was reported that in the north, where there's a high degree of freeze thaw, it's a consideration at least for that material. And going off of the second question, thank you for the question. She's asking about the shrinkage measurements in the lab in the field. So the ASTM C157 does ignore the shrinkage for the first day, while embedded sensors do account for it. Um, we saw it wasn't too big of a difference when wet cured, especially with the autogenous shrinkage. Um, and in other projects with UHPC, it is a very significant finding. As the water cement ratio goes down, it becomes a more significant effect with the autogenous shrinkage, which occurs early on. But HPC, we didn't find it to be too severe.
Okay, thank you, Mike. And Aaron, there is one question from Samer about the HCA. If you check the Q&A part, then you will see
Yeah,
his
I see the question. I think it's asking about the carbon costs accounting for trucking the lightweight from upstate New York. But I'm actually not. I'm checking the values that we had. So I think we have just the embodied carbon value, and it's based on different types of information that was provided. But I think it does incorporate for that the lightweight sand information, but I am not like 100% sure. But I think it is also considered within this analysis based on what I'm remembering.
Yeah, okay, thank you. And Mike, there are and Andrew Foden, I see your question that you are looking for the PowerPoint of this. I'll check our team and probably can share it, because the what we are presenting here will be shared, will be posted online on C2SMART the YouTube channel, so you can get that from there also. And we have another question from
Yeah, I'll
our
take that question. So thank you, Devano. So that's actually a very interesting question, and that is a good consideration. I didn't really go into too much of the very technical mechanism, but yeah, so as concrete sets and as it cures, the water inside the pores reacts with the cement. It uses it up, and it desiccates the material, is a term that's used. So it effectively dries out the pore water. Um, so when that happens, the relative humidity of the matrix decreases, and it pulls the water out of the aggregate. So it acts as a water reservoir. The surroundings effectively dry, to put it in layman's terms, and it works against gravity to pull all of this water out of the aggregate and disperse it throughout the matrix. So it allows the water to move around and reach equilibrium. So it does spread around very effectively. And the second question is, what could block water inside the aggregate? No, it does not. So the matrix, even though HPC is fairly dense, it is still permeable to a degree. So the water, especially when it's evenly dispersed with these very fine aggregates everywhere, it allows a much shorter distance that the water needs to be pulled out. If this was a coarse aggregate and there was a lot of water in certain areas, it wouldn't disperse as readily. It would just seal itself within a point But if it's an evenly dispersed sand, it very finely releases this trapped water throughout the matrix. So that's the idea really with this technology, and that kind of hit it on the head. So thank you for that.
Okay, thank you, Mike. If anyone else wants to speak up, then please raise your hands. I can allow you to talk. Okay.
If there are no more questions too, but feel free to keep typing if you are. I'm going to put in the chat the registration for the next Zoom, which is on May 26th, which is a Tuesday at 2 o'clock.
Yeah, let me share that one. It will be, yes, May 26th, Tuesday, 2 to 3 p.m. about I think this is about the X-ray bridge construction from by Dr. Mantawi from Rowan University. He is also part of our bridge research program team. So I hope you can register and join the webinar. Henny?
Yes, we're gonna have the link for that, right? And the maybe chat. I think it's already
Yep,
there.
I just sent it to the chat.
Thank you. So we also going to try to get some PDH credits. So we'll look into that. I think there has been a couple of requests to get some PDH credits for those webinars. So we are also planning to investigate that. Unfortunately, with the C2SMART being in New York, they're having difficulty issuing it for New Jersey. So we'll try to go through our continuing education at Rutgers. So for the next ones, we will let you know if we're gonna have that. And our plan is to have approximately about one webinar a month, part of the Bridge Resource Program. And I think at least one of them will be in person, but the majority of them will be online. Yeah, I think interesting question, Mike. So from your work, Mike, that you have done, would you think that using lightweight aggregate, coarse aggregate versus fine aggregate, which one has more advantage in terms of, for example, if you're using lightweight aggregate, coarse aggregate, maybe you are compromising a little bit on the strength and the other properties,
Hmm.
especially the myth about freeze and thaw. If you want to comment on that a little bit.
Yeah, so the course is typically used in lightweight concrete, so to get that significant reduction in unit weight. And you do need to treat that one as well. They do soak it just so it doesn't desiccate the material. But it hasn't really been found to provide a great, or at least not a consistent internal curing effect. It might do it locally around the aggregate, but since the aggregates are so large, in terms of their ratio between surface area and volume, it doesn't have as good of an effect as the sand, which is really where for internal curing to reduce cracking, that's where it went. And this is the same base material. It's both of it is an expanded shale, expanded slate, what have you. It's just grinded to a different size. So it is the same material, but it's for a different use case, is what it's typically been found. So you really have to kind of just pick one or the other, whether you want a lightweight concrete and have
Right.
a high degree of replacement, of course, or a little bit of lightweight sand, like, like we're seeing like 300 pounds per cubic yard and get this reduction in cracking. So that's kind of where I stand on that.
I think this is important, and I want to thank Samer from DOT. I think he's been very engaging our state and our community. So I just wanted to make that clear, the difference between the two. So lightweight aggregate could probably have the potential to have internal curing capabilities, but we haven't tested that a lot in our project. We were focusing on internally curing, which mainly use the lightweight aggregate. I mean the fine aggregate.
And that higher amount of replacement does increase the cost. So this is a balance, and this is kind of like a sweet spot. If you wanted to do everything at once, it would be a lot of lightweight aggregate, whether fine or coarse, and that, of course, bumps up cost.
And I think the emphasis, as you mentioned, is in the early ages. That's when the concrete is at its weakest and the shrinkage as it's at highest. Especially if you have a little bit higher strength HPC, you might have end up getting some desiccation, self-desiccation. So this internal curing will really help a lot with that. And I think the slabs that we tested at early age, it showed about 90% difference, which is a humongous. So this is the protection at the beginning, at the early age, is very critical. As you and those labs were maybe you wanted to mention that those were put outside, right, and under the actual weather conditions.
Yeah, realistic curing, and we tested the 7-day wet curing with the curing compound versus the traditional 14. So we saw a little bit of difference there, but that was we tried to hit as much as we can.
Yeah, I think you have more data. It's almost like a year now, right?
It's a year now, so
You
we
had
can process
156
that.
days, so maybe
Yeah.
that slide should be updated to make it more relevant,
Mhm.
I guess. Anyway, I think we're coming up to the time, and out of respect to everyone, I would like, if there are no more questions, and I'd like to thank you, the presenters, and thank all the audience who registered and attended. We had a very good number today, and I want to thank of those of you who also engaged in questions that help because this is recorded, it will help the audience, shed more light on the topic. So we'll see you. I think it's May 29th.
26th
26th.
Tuesday.
What day is it? Repeat it again, please.
May
May.
26th, Tuesday at 2 p.m.
Yes, and the link is, and please register. Use that link to register, and we look forward to seeing you at that time. Thank you, everyone, and have a wonderful day. Bye bye.
Thank you.
All right, thank you.